All over
Great.
you, Peter.
Okay. I'm going to project my stuff here. Oops. Maybe I have to share first and then project.
Yeah.
Let me try that.
Now, now it's visible, Peter. Not in presentation mode yet.
Is that okay?
It's okay, very okay.
Super. Okay, guys. So what I'm going to do is talk to you a little bit about my friend, the Indus fan. And I realize I'm being a bit naughty because I didn't even put in a map about where that is. At least, but essentially, what we're going to talk about. Let me get a laser here. Here we go. So this is the Arabian Sea in the Western Indian Ocean, and this is an isopack map of the Indus submarine fan. This is the west coast of India. There's Oman, the Murray Ridge, and the Owen Fracture Zone bound the fan on the western side. And this is a seismic profile. I think it's from Total, uh, showing showing a cross section through the through the fan, and I'm going to tell you something about how the sediment gets to the submarine fan, and what you might learn from studying that. So, some of this is very much related to source to sink influences. So, this question about how does the sediment get from the mountain source across the floodplains and across the shelf and into the deep water. And maybe not surprisingly, this turns out to be a somewhat complicated issue. But the good news here is that we have samples from essentially all different parts of the fan, sorry, of the sediment system, all the way from the Himalayas. This is Dharamsala in the Indian Himalaya, and we have samples across the floodplains in the Foreland Basin into the Delta, and here on the right you can see a bathymetry map that we collected in 2009 on a cruise with a Dutch vessel, and we took cores here in the submarine canyon, and of course later IODP sampled the submarine fan itself. So we have samples all the way that allows us to reconstruct how sediment moves from source to sink and what the deep sea record actually means. And one of the ways that we can do that is by use of things like neodymium and strontium isotopes, well, particularly neodymium. Neodymium is nice because it doesn't get affected by sediment transport, by chemical weathering processes. And although it has a little bit of an influence from grain size in this system, it's not a very strong one. So we are fortunate in this clastic system in that the different mountains that supply the sediment are actually quite diverse. So there are slices of the Indian plate itself, which form the Himalayas, that's the greater and the lesser Himalayas, as well as the deformed passive margin of India, which is the Tethyan Himalaya. And further north, we have the Khoristan Island Arc Complex and the Karakoram, which is the old Andean margin of Asia before it collided with India about 55 million years ago. And in a similar mode, we can also see there are differences across this region in terms of detrital zircon. The Indian plate material does have some similarities. For example, these two different areas both have prominent 1,000 million year, 1 giga year zircon population. But so those are harder to distinguish. But the lesser Himalayas, especially the inner lesser Himalaya, are quite unique in having a much older record here, and the Karakoram and arc sequences to the north are young. So this allows us to see where the changes in the erosion when that happens. So some time ago now, I looked at material from the delta in the record very close to the coast through about 15,000 years worth of record. And essentially, this is a deglacial record as the sea level rose and flooded the continental shelf. We could we captured that clastic flux. And not only is this a time of rising sea level, but it's also a time of intensifying monsoon. And what we found in the delta was that there was a really strong shift in the neodymium isotope composition from a relatively positive value back at the glacial times, about minus 10 and a half, up to a much more negative value of about minus 15, which is a huge variation in the space of about 5,000 years. And we saw a big change there in the neodymium, this shift essentially towards more continental values, which we interpreted to reflect more sediment supply from, well, where it rains today in the frontal ranges of the Himalaya. And we also saw this change also in the zircon populations, where we saw essentially a decrease in the population of zircons coming from the Karakoram. They were 40% at the glacial time and now closer to 20%, and essentially the opposite here in terms of the lesser Himalayas. So why do we care about this? It's useful because it means that the river is changing its composition quite substantially on relatively regular and short timescales. So it's quite easy to see where the sediment is, whether the sediment in the deep sea is associated with the glacial times or whether it's associated with interglacial. And I did also want to point out here that the time difference, the change in the neodymium compared to the change in the zircon, which is on the order of about 7,000 years, reflects the slow transport of the sandy zircon through the river compared to the suspended load of the neodymium. So, as you can probably imagine, a lot of the sediment flux to the ocean doesn't happen instantaneously. And there is quite a bit of storage of sediment in different parts of the drainage going between the mountains and the ocean. And for example, in mountain valleys, this is a example from work by Bodo Buchhagen, who showed that there was a series of terraces that formed in these valleys, quite thick sequences of storage and then release, and that this is associated with strength of the monsoon. When the monsoon is strong, you tend to fill up the valleys, and when the monsoon becomes weaker, that is when we tend to cut the terraces and they form terraces. You cut the fill. And it's not just in the frontal ranges, like in the Sutlej River. That was the Sutlej. My former student Tara Janelle looked at the Zanskar, which is on the other side of the high Himalayas. This is the high range here. She looked in Zanskar and also using OSL ages showed that also showed a filling of the valleys during the strong monsoon time in the early Holocene, followed by incision later. And working with my friend Liviu Giosan, we also found a similar sort of pattern in the foreland basin. So this is a LiDAR image of the Himalayan foreland. What you can see colored in orange here is where the big tributaries have incised themselves little valleys. So they're not very deep. They're about 10, 15 meters deep, but they're quite wide. They can be up to like 50 kilometers across. So it turns out to be quite a lot of sediment. So what we saw was accretion of the foreland in the foreland, but only in the mountain, the north side, right? Not down towards the delta, just here. We saw accretion in the floodplains here in the early Holocene, followed by incision. And actually, the same thing can be seen on the western side of the Ganges, but not in the wetter parts in Nepal or in Bhutan and over here. Probably this is a reflection of the drier conditions in the western part of the Himalayan foreland. Oh yeah, so sorry, that's a zoom up here. You can see the dated interfluve areas that were essentially abandoned around 8 to 10,000 years ago, and then the rivers cutting into them. And the Indus also flows past a rather large desert, the Thar Desert. And in places, the tar desert seems to have acted as a sediment source to the river, diluting the flux of sediment to the ocean. This is a little picture here, shows that it's a cut off meander loop, it's an oxbow lake, but you can see it's also been, it's adjoining these desert dune sands. So these were being reworked into the river until quite recently. And we can see particularly that the desert has been moving towards the west and interacting more with the river through time, particularly after about 5,000 years ago. So where's all this sediment going? Well, of course, it's going to the ocean, isn't it? So we have coring information from the Indus Delta itself. And what you can see here is a little bit of a schematic plot, but it conveys the importance here. We cored it in a number of places. And what we saw was a rapid advance of the delta, the coastline, into the Arabian Sea between about 14 and about 8,000 years ago when there's a flooding event. But as I'm sure you know, that's pretty common in many deltas worldwide. This is a global sea level rise, followed by renewed regression as the delta builds out into the ocean again after that time. And what's interesting here is the fact that this lower part of the delta was moving oceanward, despite the fact that this is a time of rapid sea level rise, when you might expect the shoreline to be moving landward. But that's not the case here, mostly because, well, because the sediment load is outstripping the the supply outstrips the accommodation space. And offshore, we see three rather large cliniforms here, a smaller western one, a great large one here on the eastern side of the Indus Canyon, and then there's a little one, a smaller one over here, the so-called Kutch cliniform. This is a seismic profile that we collected across the eastern cliniform. You can see it's pretty big. It starts here at about 100 meters below sea level and tops out at about 30. So it's a pretty large body of sediment. On the west side, you can see it's much more reduced, not so well developed, but it is still a decent amount of sediment. It's about 20 meters thick. And as you say, it's about 40 kilometers, building out for about 40 kilometers from the coastline. And then we have sediment in the canyon itself. It turns out that the sea level rise doesn't entirely cut off sediment supply into the deep water. We have a series of cores that run down the canyon. The one right at the bottom that was collected by workers from Utrecht, Martin Prins and George Postma looked at. What they were showing is that there's essentially the fan itself is abandoned about 10,000 years ago, but the submarine canyon itself actually, as far as we can tell, continues to receive turbidites, and not particularly thick, but there are continued mud and sandy turbidites are being delivered all the way through the rising sea level and the present day high stand. So this is a little bit different from the Bengal fan, right? So the Bengal fan continues to accumulate sediment in the deep water through the sea level rise. That's not entirely true here. The sediment makes it into the canyon, but not much further. So we can tell a little bit about where that sediment is coming from if we consider those isotopes I mentioned earlier. So if you look at the one plot on the right here, strontium against neodymium, you can see that the Indus River in the glacial phase has a much lower strontium 8786 value compared to the more recent. This is essentially the value for the last 8,000 years. And what you can see here, there's as I showed you before, there's an evolution here in the early Holocene. What's interesting to note is that the sediment in the canyon is all clustering around this Holocene, late Holocene value, and not the glacial or early deglacial value. So that means the sediment getting into the canyon is essentially coming directly from the river mouth. It's not being reworked from older glacial sediments. seems to imply a rather direct connection between the sediment in the canyon and what is being discharged from the river mouth. Now, it is worth bearing in mind that these data are dominantly fine-grained sediments. If we consider the sand, however, we look at that with zircon ages. So, sorry, this is a slightly painful diagram, but essentially the y-axis here represents time, with the youngest material at the top and the oldest at the bottom. And the x-axis reflects the distance offshore. So here the river mouth is, the present river mouth is up here, and the older material in the canyon is down here. So each of these colors represent different populations. The blue ones represent erosion from the Himalayas, and the yellow from the Karakoram. So there's a couple of things to note here. One is that similarly aged sand in the delta actually looks quite different from the sediment in the submarine canyon, right? There's a lot of Karakoram material here, which we don't really see over here, much less. The other thing to note is that there is variability on quite short timescales. So, for example, up here we have an appearance of this pink material, very young, 20 million year old grains, possibly from Nanga Parbat, which is the Western syntaxis. I'll come back to that in a little bit later. But the important thing to note is that the sediment is not, it's not being homogenized by transport through the floodplain. So there are pulses of unique erosional signals that we can see in the canyon, and these span something like about 200 or 300 years. But there is a disconnect here between the river mouth and the canyon itself. And so this leads us to think that the sand, well, I'll show you a little cartoon in a second. Yeah, let's just do it now. What that means is that there is a disconnect that tends to be dumped near the river mouth, whereas muddy material is being transported both onto the cliniform during the high stand, as well as into the submarine canyon, where it falls out as some of it as hemipelagic drapes. So if we do a little sediment budget, we can essentially add up all those major depot centers. So about half of all the sediment actually lies under the delta plain, and in the lower part of the alluvial plain, and about the other half of the sediment is being deposited in the offshore, mostly in those big cliniforms I showed you. Only a tiny fraction of this is going into the submarine canyon, right? Just a really tiny, really small amount. So there's very little deposit in the deep ocean during the high stand, during the interglacial period. And actually, we can have a little bit of fun with these numbers, because if we know the total amount of sediment that has been deposited since about 14,000 years ago, that means that we've received something like almost 1.2 gigatons per year, which is actually an extremely high number, because people like Milliman and Farnsworth estimate only about less than a quarter of that, 250 megatons per year in pre-industrial. Some people have picked slightly higher numbers, but even the earlier work that suggested somewhat higher numbers are not even half this long-term average. So what this suggests is that there used to be astronomically high rates of sediment supply during the early part of the Holocene. And we can also, by figuring out how much sediment has been eroded from the floodplains, we can also see that only about that 75% of the sediment that's deposited during the Holocenes is not coming out of the incision of terraces or floodplains. It reflects erosion of the bedrock or recycling from moraines. So this is, I forget what the correct name for this is. This is what my friends like to call a fat arrow diagram. And you can see during the Holocene, essentially where all the sediment is going, half of it into the cliniforms and the other half under the delta. Most of that sediment is coming from the mountains, from bedrock erosion and the moraines. About 11% may be coming out of the floodplains. So let's think about glacial times. How is the glacial Indus different? Well, we have some sediment here deposited as shelf edge deltas during the falling sea level stage. You can see these are imaged by Sparker profiles on the outer part of the shelf. And of course, in the deep water, we have beautiful submarine channel complexes, channel levee complexes that were detailed by mostly by industrial seismic some years ago, as well as further out to sea fan lobes of more distal material, finer grain material. So this is an overview. You can see the various deep sea channel levee complexes, which fortunately we know how long they are, we know how thick they are, so we can make an estimate for how much sediment has been deposited in them. And we can play the same sort of game as I did with the Holocene. So we know what the different volumes of sediment are. You can see the shelf edge deltas are fairly small. We have submarine fan lobes, channel levee complexes, and it turns out that this number is actually remarkably similar to the amount of sediment that is eroded and delivered to the ocean, or at least close to the ocean during the high stand period. So actually, most of the sediment we can also calculate, since most of the sediment here is going into the deep water. We also have some idea that most of that material is being eroded from high stand deposits, right? So what that means is in the glacial times, where most of the sediment is now going into the Indus Fan, it's partly being derived. Significant parts of it are coming out of the cliniforms on the shelf, which is then exposed. It's being eroded out of the delta plain and the alluvial plain. But the punchline is that like 75% of this stuff that reaches the ocean is not eroded during glacial times. It's actually eroded during interglacial times, but it only gets redeposited into the deep water when the sea level falls, and we can make a connection there between the shoreline and the deep ocean. And I'll show you a little bit of evidence for what this means. What this really means is that most of the clastic record reflects erosion when the monsoon is strong. We see this in the younger cores, the Pleistocene cores that were collected by IODP drilling in this region, actually almost exactly 10 years ago now. And so in 2015, we drilled the Lakshmi Basin. The Lakshmi Basin is positioned here on the east side of the Indus Fan. It's separated by a thing called the Lakshmi Ridge. You can see it here. It's a little fragment of the Indian craton that has been rifted off. This little basin is a bit strange, but it essentially opens before the main onset of seafloor spreading in the main Arabian Basin. And we were able to core this through until the Middle Miocene, particularly, well, in this site, 1456. The eagle-eyed here, something I'm not going to talk about today, actually, but this pale-looking thing here is a gigantic mass wasting deposit. It's actually the second biggest mass wasting deposit known on modern passive continental margins, but maybe that's for another day. But it did not help us get a continuous fan record, shall we put it that way. So most of our record spans about 11 million years. For what that's worth, that is sort of roughly equivalent to a lot of what we see in the Shiwaliks in the foothills of the Himalayas. But rather, it was good that it does span, however, the strengthening of monsoon winds and monsoon related upwelling in the Arabian Sea that was documented in the late 1980s by people like Dick Kroon. We do have unconformities in here, which are pretty well dated, but we have a relatively good record here through to the early part of the late Miocene. And again, we can play our game with the strontium and the neodymium and see where all that sediment is coming from. Well, this little scatter plot over here, neodymium against strontium isotopes, the new deep sea deposits plot in blue, which is essentially sitting here on top of the brown is the Holocene part of the Holocene record, and we also um, you can see that it is very similar to the Karakoram, but because this is a mixed signal, we can't really tell uh, what the relative proportions coming from things like the Trans-Himalaya or even the Deccan Plateau versus things like the Greater Himalayas, and the Lesser Himalayas are even more extreme. So if we just focus on neodymium isotopes and we do a sort of a smoothing analysis here, the blue are the new IODP records, the brown comes from this well, Indus Marine A1, which is an industrial well on the continental shelf, but which goes back into the mid-Miocene. And we were able to exclude some of these higher value plots here. I did it rather unwillingly when we first did the analysis. We were worried about that these were contaminated by erosion from peninsular India, particularly from the Deccan Plateau. Subsequently, I have repented, and I actually really believe that those really are derived from the Indian peninsula. So this yellow shaded band here reflects the true Indus River flux. What you can see is it becomes gradually more positive up section between about 16 and around, or 5 or 6, and then it begins to decrease. So the modern river is like up over here. It's undergone a substantial decrease here. Oh, and this is just the Indus related plot on the side here in the gray. So we see like long-term evolution in where what the source of the river sediment is that we can deconvolve there. And before the onset of the Pleistocene, of course, you can see the range of the Pleistocene, the glacial cycles, glacial to interglacial. There's actually a huge variation here, much more variation in glacial cycles than we saw in the mid and early and late parts of the Miocene. But as I said already, basically, if there has been variation, it tends to be biased towards times of strong monsoon, mostly eroded during interglacial times. And we can also look at this with zircons, right? This is just a subset of what we got. So these are zircon uranium lead ages. These are all the various possible sources and the recent delta here, and these are a selection of some of the material from the submarine fan. And it is interesting to note here that all of those sediments have a rather prominent young peak that I've highlighted in blue here, and which is associated with erosion from the Karakoram. It's interesting to note also that this yellow peak, about 1.8 billion year peak, really only appears in the turbidites about 2 million years ago. And that peak has its strongest similarity with the lesser Himalayas, right? Actually, also the recent delta as well, right, but not the glacial delta. So this suggests to us potentially that the lesser Himalayas were not available for erosion until about 1.9 million years ago. This is a somewhat controversial topic because a lot of people will tell you that the lesser Himalayas began to form about 10 million years ago. And that may be the case, but this data does suggest that they weren't being very heavily eroded until much more recently. So let's skip over that. It is interesting to note that this is a structural reconstruction by Alex Webb. And what this is purely structural geological interpretation. It's not based on the clastic record at all. So this is what it looks like today. And it is interesting to note that the purple rocks, which are the lesser Himalayan ones, he shows them still buried at 5.4 million, but then exposed by about 1.9. So our clastic record in the submarine fan seems to be consistent with that. That's sort of encouraging. One other thing that we were worried a little bit about was about the syntaxis. So the Western Himalayan syntaxis, this is Nanga Parbat. It's an 8-kilometer peak. It's essentially a metamorphic core complex. This is a picture of Nanga Parbat, and the main strand of the Indus runs past this. So, if you're not familiar with the geology of the Himalaya, it's where the Himalayas undergo this big bend. So, the arc of the Himalaya bends around Nanga Parbat before sweeping south. And there's another one over here, the Namche Bawa syntaxis. So the reason that this was worth worrying about is because people will happily tell you that the Brahmaputra is like 60% or so derived from erosion from the Namche Bawa syntaxis. Well, that's great and all, but if you want to use the Bengal fan to look at the evolution of the Himalayas, you might find yourself out of luck because if it's swamped by erosion in the syntaxis, then the record is not representative of the mountain belt overall. So we were a bit worried about the effect of what happens to the Indus River as it passes Nanga Parbat. It has recorded extremely high uplift rates, something like 10 kilometers per million year. So we had a look at that and we looked at zircon. These are zircon plots. By the way, these dimensionless diagrams are so-called multi-dimensional scalar diagrams, and basically if the little dots plot next to one another, it means they're very similar in terms of zircon. And the Indus River downstream of Nanga Parbat, this is at Atok here, actually does plot quite close to, this is this place Tato up here, and there's another thing. These are regional streams that are derived from the Nanga Parbat Massif. And so we saw some similarities here. For example, if you, that's Nanga Parbat, Gorikot, and Tato, which are actually quite different from the basement rocks that were previously looked at. And you can see here there's at Atok downstream of the mountain, we have this prominent 100 million year peak. We see it again at Tato, but we also see it in the Karakoram further north in a place called Skardu. So this is a bit ambiguous. My colleague Chris Mark decided to point his trusty laser at rutiles instead to see if they would do a better job, and they do. So again, here, this is the downstream plot. This is a place called Tarbella, which is a little bit further upstream, but it's close to Atok. What you can see here, there's the rutile ages are plotting at about 10 million years ago. The detritus from Nanga Parbat itself is somewhat older, more like 25 to 30 million years old. But the better match here is with the Karakoram in Skardu. So we think that actually most of that sediment in the Indus River, it's not being dominated by the syntaxis in the way that it is in the east, but actually only about 10% of the sediment reaching the ocean is from Nanga Parbat. In fact, the most important source is the Karakoram, which is what had been inferred from the other provenance proxies. No, we'll skip that. That's less important. This is the long-term evolution of erosion with the different source regions here. And what you can see, the expanding blue stuff here just shows you how much more important the Himalayas are getting through time, how they're expanding their influence with the loss of erosion from the Karakoram, presumably because of uplift and exhumation caused by that summer monsoon. So I just want to finish my talk here with a few words about climate and whether you can derive climate from these deep sea records. So in theory, of course, although the sources are the same, the weathering processes are a bit different compared to whether it's a dry climate or a wet climate, and especially like a tropical climate. That doesn't stop people trying to measure rainfall in all manner of different weird and wonderful ways. This is a compilation I did from the South China Sea, where people used hematite and goethite and magnetic susceptibility and titanium calcium ratios and you name it, and they're all a little bit different from one another, which is a bit disconcerting. I find people looking at monsoons, it depends on your favorite proxy and even where the drill site is located, about which one they like to use, which feels not great in my opinion. I have become a fan of hematite and goethite because a lot of this data is collected routinely, or was, collected on the JOIDES resolution rather routinely by spectral camera. So that means we can look at this in all drill sites, and I tried to do that. So this is a selection actually across Asia. This is the Indus, the Bengal, the Mekong, the Pearl River. And there's a couple of things to note here. First of all, the Pearl River makes a nice sort of coherent pattern here with high values here in the mid-Miocene and a reduction. The Indus is a bit rattier than that. I mean, I guess it's much more noisy. It rises up a little bit and then comes down. The Bengal fan data is a complete dog's dinner, as you can see here. And the reason for that is because actually the camera wasn't working properly. So it turns out that a lot of these Asian legs, if you're interested in this sort of data, you have to go back and measure it again. So I decided to cheat because it turns out that the redness, the A star value of the color, is actually quite well correlated with the hematite abundance. And you can use this as a shorthand. So apparently even the broken camera measures redness quite well. And again, you can see the Pearl River has this distinctive shape with a peak monsoon here in the mid and early Miocene, and then a decrease. Interestingly, the 90 East Ridge in the eastern Indian Ocean also shows an early peak and then a decline. The fact that this one begins to decline a little earlier, more like 12 or 13 million and not 10, suggests that the East and South Asian monsoons are a little bit decoupled from one another, but that both of them have weakened since the late Miocene, probably because of global cooling. Unfortunately, the punchline for this is if you want a nice climate record from the deep oceans, you should stay away from submarine fans because unfortunately, there's really not very good or coherent trends either in the Indus or the Bengal fan here, and that you're much better off with a hemipelagic record. So why that is, I'm not sure. I'm going to guess it's related to recycling and reworking on the submarine fans, but I wouldn't pick a submarine fan to go looking at paleoclimate if I were you. And so, yeah, I tried to put all those sort of data together and make a little compilation whether I could make about how the monsoon has evolved since the mid-Miocene. I mean, broadly speaking, it's a drying trend. It's not entirely coherent, consistent. Some places like Indochina dry much later than places like the Western Himalayas. But in general, as the Earth is getting colder, we seem to get weaker monsoons. And we also see that the Australian monsoon is decoupled from its Asian colleagues, even though the East Asian monsoon migrates essentially into the Southern Hemisphere in the present day. It seems the Australian climate is much more linked to the closure of the Indonesian through flow and the drift of Australia north into more tropical climates. So I will be quiet in a minute here, just to sum up a little bit. I hope I showed you that the deep water record can tell us a few things about erosion in the Western Himalaya and the monsoon. I hope I showed you that the monsoon is a key control on the flux of sediment to the ocean. It determines when the erosion happens and it controls the amount of recycling and the speed of transport of sediment through the river. 75% of the sediment that ends up in the Indus Fan is eroded not during the glacial times when it's deposited, but during the interglacial times. So there is some buffering of sediment on the floodplains, or plains, not plates, but the original signals propagate to the coast. So in the present high stand, we can correlate between sediments in the delta and climatic events during the Holocene. But that doesn't last because when the sea level falls, all of those high resolution records are essentially mixed together and thrown into the deep ocean. So what you end is a smoothed record in the submarine fan, dominated by the climate of the interglacials. And when we apply these lessons to the long-term record, you can see that these provenance proxies are showing more erosion from the Himalayas since time, less from the Karakoram, and especially a big increase in relatively recent geological times from the Lesser Himalayas. And unlike our friends in the east, the western syntaxis, the Nanga Parbat Massif, is not dominating the submarine fan. The fan is recording the climate across the western Himalayas and its floodplains. So it's a relatively good place to look at the evolution of the mountain belt. Yeah, and that actually these provenance derived data are consistent with independent structural models, which is sort of encouraging. Now, just to finish here now, I'm going to have a shameless advert here. I happen to be the editor-in-chief of Geological Magazine, which is a sort of a broad spectrum solid earth journal, and we would love to get sedimentology papers from the people who are attendees of the Drifters seminar group. So please bear us in mind next time you have a paper in mind. Thank you very much.